Alright, welcome back. This is Chapter 8, Part 3. Alright, so Module 11. And so we're going to go ahead and start talking about the resonance structures. So we just looked at some Lewis structures in Part 2 and how to draw those. And one of the things we need to note is that a single Lewis structure may not adequately describe some molecules. Okay, and so an example of this would be ozone. Okay, and ozone is actually just 3 oxygen molecules connected. Okay, but when you draw the Lewis structure for this, one of them has to have a double bond. Okay, so which is right? If we have a double bond between this central oxygen and this oxygen, or the central oxygen and this oxygen? Okay, well, the actual structure is going to be a combination of these two. So the electrons are actually not localized into a single area like here. Okay, they're actually delocalized, which means they're kind of shared over this whole area. Okay, so both of these are equally valid, both of these structures. So we can think of resonance structures as basically combining blue paint and yellow paint, okay, which would just combine to make a green paint, okay? And so by mixing these two resonance structures, okay, we basically get these overlapping superimposable images right on top of one another, and so the actual ozone molecule is kind of a combination of the two. Well, it's also possible to draw multiple Lewis structures for the same compound, okay, but you should remember that usually only one of those is correct, okay? And so to determine the correct structure, we have to calculate what's called the formal charge on the molecule. So to calculate the formal charge, we look at each individual atom, okay, and determine how many valence electrons that atom has, okay? So we look at our atom, we determine the number of valence electrons. Then we just subtract out the number of electrons in the actual Lewis structure. And the number of electrons in the Lewis structure can actually be calculated. It's a bit tricky, but it's basically taking the sum of all non-bonding, so any unshared electrons, which are just the dots around that Lewis structure, okay, and basically adding that to half of the bonding electrons. So for every bond, we take 1 electron. Okay, so half of those bonding electrons. There's 2 electrons in every bond, but we're going to take half of those. Okay, and that tells us the number of electrons in the Lewis structure. So if we take the number of valence electrons and subtract it from that number, we get the formal charge on that atom. So after calculating the formal charge on each individual atom in that molecule, we can actually determine the best structure, best Lewis structure, based on 2 rules. The first is that the atoms bear formal charges closest to 0. Okay. So the closer these are to 0, the better the Lewis structure. Secondly is that any negative formal charges you have are actually on the most electronegative atoms. Okay. Now, these last 2 notes are very important. Okay. And so one is that formal charge does not represent the actual charge on an atom. Okay. So make sure you remember that formal charge is different than the actual charge on an atom. Secondly, is that when you calculate these formal charges for different Lewis structures, you may have something that's, like carbon dioxide or CO2, 2-, or if you have an overall charge on that entire molecule, then the sum of all the formal charges on each individual atom should equal the net charge on the ion, right? So if you have something like H2O, it has no charge on that molecule. So the total charges on the H2O Lewis structure for each individual atom should also be 0. Okay, and you can see that in some of the examples in the practice problems as well. Okay, so once again, I encourage you to calculate the formal charge on these different atoms or on these different molecules so that you understand how to assign them. Now, as I always say, there's always an exception to the rule. There's exceptions to the Octet rule, and there's actually 3 of them. I'm not going to spend a lot of time reviewing these rules in this lecture, but you should spend time reviewing it in the book. Make sure you know these rules because you will encounter a number of problems that will require you to know these, okay? And so there's basically 3 of them. You can read over these slides and clarify that as well. The last part of we're going to talk about, and we're going to do very quickly, is the strength of a covalent bond, okay? So we can actually measure the strength of a bond by determining how much energy is needed to break the bond. Okay, and this is what we term bond enthalpy. The bond enthalpy for a chloride-chloride bond, like shown here, okay, is 242 kilojoules per mole. Okay, and we actually put this little italic capitalize D in front to say this is bond enthalpy. Okay. So, excuse me. In a polyatomic molecule, though, there's multiple atoms, right? So here we have a polyatomic molecule. There's multiple atoms, okay, and there's multiple bond enthalpies. There's a bond enthalpy for each carbon-hydrogen bond, right? And so this is methane. It's a good example. And if we look at the total bond enthalpy of this, it's 1,660 kilojoules. Okay. Well, for each carbon-hydrogen bond, we can calculate that that means there's 4 of the carbon-hydrogen bonds, so each one is about 415 kilojoules per mole. So when we talk about average bond enthalpies, you'll be given a table like this on either homework or on an exam, okay, and you may have a structure that you have to determine what are the total bond enthalpies. Okay, so if you had something that was 1 carbon, 1 nitrogen, 1 oxygen, and it was a carbon bound to a nitrogen and a carbon bound to an oxygen, you could add up these two average bond enthalpies for carbon, nitrogen, and carbon, oxygen in order to calculate that. So another good example of what kind of question you'll encounter is you may be asked to calculate the overall enthalpy of a reaction using these given values of bond enthalpies. Okay, so here you may be given that methane reacts with chloride to give you CH3Cl and hydrochloric acid, and so you need to calculate what is the total delta H of this reaction. Well, we just take the sum, we add up all the bond enthalpies of bonds broken, so we draw out these structures, okay, and then we look at what bonds are being broken, subtract those enthalpies for each one, and then we look at the bond enthalpies formed, so we look at our products, add up the bond enthalpies of bond formed, and we can then calculate the delta H of the reaction. Okay, to really clarify this concept and a lot of the stuff in this chapter, chapter 8, you really need to watch those practice problem videos and really work through some of the problems to really clarify some of these. There's certain rules that you apply. Once you see some of those examples, it'll help you definitely understand this chapter a bit more. So that concludes chapter 8. Just 2 more chapters left in the semester and we're done. So good luck.